welcome everybody. Thank you for making the time to come down here tonight. We're not a very big group tonight, but I'm very happy to have Mike Gardner here from UC Davis to talk to us about some of his research. So before we get into that, just quickly introduce myself for those of you that don't know me. My name is Alex Forrest. I'm currently the interim director here at TURP, taking over for Jeff Schlada, many of you know, many years. And I'm excited to continue the speaker series. I'm excited to continue what we do here at TURP. So if you guys have questions or feedback, please feel free to pass it along. I'm always happy to talk about it. So today, before we get into things, just a couple things to go through that Allison handed off to me. So on May 30th, we're doing an auctions for feeding healthy pets here at Sunnyside. So feel free to come down to that. We'll have more details about that. That's through the UC Davis School of Vet Med, so veterinary medicine, to look about customized plans for your pets. Then we're also, and the final date is to be confirmed in May. We'll be doing a movie night for Common Ground, narrated by Jason Momoa. And it discusses the use of regenerative farming practices as a way to mitigate climate change. This movie night will kick off our participating in Grow Your Own High Elevation Garden workshops that will start off at our Tahoe City Field Station on May 31st. Is that right, Austin? Yep. And then another quick shout out for Turk Cirque coming up this summer. That I know is being a great hit so far, and many of you have already participated in it. And so from June 17th to the 23rd, we'll be doing our 4th annual Turk Cirque via kayak. And so for those of you that haven't tried it or any segment of it, I'd certainly encourage you to come out and participate in it. It's a great activity for us all to join. So I know Tim wanted to stand up and give some quick comments, then I'll introduce Mike.
Don't look into the light.
I can tell.
Over here. Hi, I'm Tim Kosher. I'm a docent, got my docent outfit, gave tours over at the Science Center this morning. 6th graders studying things about Lake Tahoe, but I'm also on the advisory board. And so the advisory board, to be clear, is not to give advice of what science that UC Davis and TURP is doing. It's to raise money to pay for the science that's being done. So I'm here to represent the board to let you know that even though we get, money from UC Davis to fund things, and they write a lot of grants and gets funding for a lot of projects, but philanthropy fills in the gaps, lets us be much more responsive to things. And so I'm going to encourage you to you can go on the website. We got Tony back over here who's works for UC Davis. We're glad to talk to you or me, and just encourage you, if you've got the means, we'd sure appreciate contributions. Thank you.
All right, thanks, Tim. And the other people I'd like to thank are Allison, who did the organizing tonight, and Heather, who can't be here tonight, but he's doing well. And also the AmeriCorps sitting in the back there, we're at the front table. So Logan and Melvin and Sarah for making the time to come down here and help organize all this. So it takes a team to make all this happen. So I really appreciate that. So Mike Gardner, I asked him to do a little blurb. So they sent me along a blurb here, so I'll just read it verbatim. So is a newly acquired assistant professor at UC Davis. So he started in July. In the Department of Civil and Environmental Engineering. He's about 3 doors down from where I am. And he received his Bachelor's of Science in Civil Engineering and his Master's and PhD in Geotech from Berkeley. And then before joining UC Davis, he was a faculty in the Department of Geological Sciences and Engineering at the University of Nevada, Reno. So this is relatively close to home for him. But now his new home is in Davis. So it's a bit of a change of scenery. And worked as a postdoc at the Neary Sim Center, where he developed software for natural hazards engineering. However, prior to pursuing his graduate studies, he worked as a geotech engineer in San Francisco. And prior to attending the university, he served in the U.S. Army as a combat engineer. And his professional and research interests include geological engineering, rock mechanics, natural hazards engineering, and the application of numerical and stochastic methods to shallow earth processes and engineering analysis. Originally hailing from South Africa, he has traveled far and continues to grow his career and his path. And I did ask him to give me a fun fact before starting this. So his fun fact for us tonight was he's been continuing the same sourdough starter since 2013. That he actually got from a starter that was on the Oregon Trail. So he enjoys backpacking and being with his family and going into the mountains. And so I'm looking forward to hearing his talk. So thanks, Mike. Take it away.
Thank you. Thanks. Thank you for the introduction. I guess based on the writing, I'm no Barbara Kingsolver, but it's all right. Thank you very much for having me. And so today I'll be talking about infrastructure resilience in the face of extreme flooding. You can hit the next slide, Alison. Thanks. So just an overview. I'm going to give you a bit of a background about extreme flooding, talk about costs and insurance, which is a very maybe interesting topic, maybe not. And then I'll talk about some specific disasters that I've been involved in with post-disaster reconnaissance, the 2021 Western European flooding. And then I'll talk also about the Yellowstone floods that happened in 2022. Then will be more about some comparisons between what we saw in Germany and in Yellowstone, some similarities. And talking about looking at this more holistic interaction when flooding events happen, and then just kind of some ideas about how to move forward and meet these challenges. So if you look here, this is just showing for 2021, globally what the natural hazards were or natural catastrophes. And if you look at the green and blue dots, you'll see there's many, many more of them. So the vast majority of natural catastrophes that occur annually are these meteorological or hydrological events that end up costing billions of dollars. I mean, the earthquakes are a big deal, but they don't happen as much. And so next slide. So if you look at 2021, if you look at the top 7 costliest natural disasters, you can see here you've got Hurricane Ida, you have the flooding in Europe and winter storms, some more flooding, and then you start getting into earthquakes and tornadoes. So, you know, the vast majority of the cost comes from these flooding hazards. And I don't know if people knew, this for me was a new thing, if you know about reinsurance, which is insurance for insurance, which for me was a new thing. It kind of, it smacks somewhat of The Big Short, like at some point, someone's insuring someone, and when something bad happens, who's paying? So you look at this uninsured versus insured losses. For me, which was an eye-opener, and I've barely dug into it, but there's a lot of really good data on natural disasters coming from reinsurance companies, so they can hedge their losses, I guess. So anyway, so next slide. And so what I want to show you here is just in terms of global damage cost for floods. You can see that things have gone up a lot since the 1980s. And I mean, there's numerous factors involved here, but the point is that you cannot ignore that these things cost a lot of money. In the US, NOAA estimates that it costs about $8 billion per year annually in flood losses. So not a cheap thing. And if you look also at floods, so there's big catastrophic floods, but then there's also floods that happen that don't necessarily make like global news. But if you look at the aggregated losses from flooding, they make up the vast majority of losses compared to larger events like earthquakes or so. So really, in terms of impacts to society, flooding and these hydrological or meteorological events are a substantial economic impact on society. And so here, I just picked the local event, 1997, flooding in Reno. So here, so if you're familiar with downtown, like Wigfield Park's right here, underwater. And this is the worst flooding since 1955 that they got. And I think FEMA also, there was this statement in one of their documents that's saying the type of flooding that was received here would be something that would almost never happen, which they probably regret those words. But if you look here, you can see Wingfield Park, that thing's pushed over. And then I think the east-west runway at Reno Tahoe International was knocked out for like a few months. plus. So, and this was what, like about $700 million in cost. 2 people died, 35 people injured. So it's not a small event. And so this was in 97, but you know, if you walk in downtown Reno, you wouldn't think that you're at flood risk there, and certainly not based on where properties are sitting. So, all right, another recent event and a similarity between, this is Orville Dam in Northern California. For Reno, similar for what happened at Orville, you had a pretty large snowpack hanging out in the mountains, and then you have these warm rain, like warm moist systems moving in. You get warm rain on snow, so you get much more runoff. And in many cases, the soil is already saturated, so you get a substantial amount of runoff. And a lot of these reservoirs are designed in terms of their operation based on historical data, which in the face of climate change is, if you're basing it on historical data, you're not capturing these changes in impulses. And so this near disaster was the first time in the history of the spillway that they actually spilled water across the emergency spillway. And so it initiated with one of these concrete panels getting plucked in the main spillway there. And so I did a bunch of numerical work on that. I won't really talk about that today, but if you want to talk numerical analysis of scour and erosion, that's something we can talk about as well. But so anyway, the point is that it happened there, and then they started spilling across the main surface spillway, and they quickly had these erosional features moving up toward the emergency spillway. And you can see here that if this thing keeps eroding and that emergency spillway goes, now you've got a real disaster. So at that point, they just let it rip down the main surface spillway. I think 188,000 people downstream of the reservoir had to be evacuated. So they got, in this case, I mean, it's pretty close. That's pretty close to being a disaster. But anyway, so similarities between these events. Next slide. And so when these kinds of events happen, when you have these extreme events, there's this association called the Geotechnical Extreme Event Association, or GEAR, which is funded by NSF. It's a volunteer organization. So if there's some type of natural disaster that occurs, it's focused on the geotechnical engineering aspects. You know, people from industry, from research, all different walks of I guess of this field, volunteer their time to go and gather as much perishable data as possible so that we can learn from these case histories. And the point of it being that all the data that's gathered is released publicly, the report is released publicly so that people can use these well-documented case studies to learn from and design essentially for the future. Also, I should have checked earlier, can everybody hear me okay? Or do you want me to use a mic? Okay, cool. So essentially learning from bad things happening. And so GEAR, initially, if you look at the types of disasters that they responded to, you see a lot of red for earthquakes. So GEAR used to be the Geotechnical Earthquake Event Reconnaissance Association, but with this change, or I guess more of a focus on looking more broadly at natural hazards, now it's extreme event. So when I talk about Yellowstone and when I talk about Germany, these reconnaissance missions were funded by GEAR. Yeah, sure.
When you don't see any disasters in Australia or Africa or Brazil, is that because they don't have it or they don't have a volunteer?
So what happens is, so for GEAR, and there's a steering committee that decides on how things go, and there's usually someone expresses interest to go and look at these things, and then a team goes. So for a lot of these, so for example, in Australia, there's, I'm sure with the flooding and so that occurred, there's many local researchers that went, but a US team was not deployed. And I think in this case, I mean, now you're getting also at a different thing. The fact that Africa is left out is rather not so good from the fact that natural disasters occur in Africa as well. But that's a separate topic. But yeah, it usually takes somebody saying, let's go. We want to get this data. And so when we went to Germany, there were 2 German faculty that led the mission. And so it's, yeah, so somebody has to express interest. But certainly, I wouldn't use this as a map of likelihood of a natural hazard occurring. I'd use it as a map of a natural hazard occurring and somebody caring. That's in the US. Somebody caring that's in the US, I should say. So anyway, all right. So if we talk about the flooding in Western Europe, so this is in 2021. This is probably one of the worst flood disasters in recent history. In Europe, you can see there's over 230 people died, 46 billion euros in losses. And if you look here, this is showing two towns. So this is the town of Schuld, where a large portion of this town was just wiped off the face of the earth by the flooding. If you look here, this is Altenaar. You can see this area was inundated entirely. We'll talk more about this a bit later, but it's certainly I think the most destructive flood on record for Europe. Next slide. So just to orient you, so here's Germany, you've got Belgium, Netherlands up here. And so what I'm going to be focusing on is primarily this R Valley, where you can see the R runs through here and runs into the Rhine. And then I'll also talk about some of these spots that you might have seen in the news, more like the gravel mine in Blessem and Steinbach Dam. So just so you can orient yourself as these names come up. Okay, have folks seen this photo before? I feel like this is kind of like, no, okay, so this is Blessem. What's it? You've seen it? Okay, right. So this is Blessem or I guess the Blessem district. And if you look at this, the river that caused this massive amount of erosion is actually running right here. It's more of a little creek. And so you have this massive amount of inflow coming in. Again, the ground's already saturated. There was the super system that came across Europe and essentially stole across parts of Germany, Belgium, and the Netherlands, and just dumped almost a year's worth of rainfall in the course of a few days. And so here you have this tiny little creek that can't really carry the water, or at least it breaks its banks. And then you see here's this overflow, and you can see these head-cutting erosional features, which are a few meters high. And if you look a little more closely, the reason this erosion happened is there's this, so when we look before, we're kind of looking this way, the river's running here, and downstream is this gravel pit that was empty. And so once the water starts flowing over, it goes into the pit, and it's flowing over the edge of this thing and just cuts its way back. And so these are very loose colluvial deposits that are very easily eroded. So it just chewed its way back here through the town. So if you look here, this is showing some of the damage where, here used to be houses. Those are all gone. You can see some utilities exposed here. And just the height of these for scale, I mean, that's several meters tall. And so another example, so Steinbach Dam. So this actually, so I should mention when we were in Germany, we weren't allowed to fly drones. The German military forbid it. And because of this, the reason this happened is there's actually geohazard tourism, where people were driving out to this part of Germany to fly their drones to hope to get a picture of when the dam fails. So the Germans had enough of that, and they pretty much grounded all flights. But so this reservoir was pretty close to failing. It's I'll show you a picture of that in a second. But so this was built in 1936. It's about 26 meters tall. It's a rock-filled dam. On the top of this is this asphalt roadway, and on the upstream side, the impermeable barrier is also asphalt. So this is what the dam looked like shortly after overtopping. Stop. Oops. There we go. All good. Motion sickness, anyone? Oh yeah. So you can see here it overtopped, and you can see these erosional features. And here, this after the fact when they drained it, you can see quite a bit of erosion happening here. And so it overtopped for approximately 3 hours. When you look at rock-filled dams, usually if they're overtopping, that's the worst thing that could happen, right? And they'll fail anywhere between 15 minutes to maybe 2 to 3 hours. And so this dam survived in this case. And the fact that it survived is largely due to this asphalt roadway going across the top, because this rock-fill material is relatively easily erodible by flowing water. And downstream of the dam, there's a number of towns. There's a town called Iskirchen, if I'm saying it correctly. And so if it went, there would have been numerous towns inundated downstream. So this dam, I think originally was put in place for, I think it was textile factories or something like that in the town. And so it's been in place there, yeah, it would have been a town of several, like several thousand people have been gone. So I mean, that's, Yeah, this one they got lucky because if that asphalt wasn't there, it probably would have been gone. Okay, and so one thing also with this dam is that the intake, and actually if you can go back a slide real quick, I should point this out. So you've got the spillway intake over here, and here's actually where the spillway, the intake's here, water spills out here. And here's this lower intake as well. And so during the event, these clogged. And so if those spillways are clogged, the intakes are clogged, you can't really release water to get the reservoir level down. So they were undersized, and so yeah, led to the overtopping. They couldn't spill enough water to keep it stable. And so here's just taking a closer look at the material. So this is this rock-fill dam where it's rock mixed with clay. This is pretty clay rich and relatively easily erodible. And if you look at this, you can see really this material wants to go, but this asphalt roadway sitting on the top, it's kind of like this erosive layer, like almost if you think about mesas or so, where you've got the erodible layer sitting on top, that kind of helps protect things underneath it. Okay, so here we collected some remote sensing data. These were just LiDAR scans with an iPad, which was pretty cool. You just kind of stand with the thing and it creates this 3D model. So we can map these erosional features. And then also using drones to create these 3D models, so we'd actually do some geometric analyses. But when you look at this, so because it's rock fill mixed with clay, you get this specific type of erosional feature here, where the water flows over, it steps, digs down, creates a scour hole, steps, digs down. And this is indicative of scour or progressive scour in a more cohesive clay-like, silt-like material. Another thing that saved the dam here, and so this is, you can see again after the fact we were there, we collected some drone imagery, and with that drone imagery you can create these 3D models that allow you to extract three-dimensional features of whatever you're mapping. So in this case, this dam. So if we look at the crest elevation, you can see that the crest is also relatively flat. And so if you think about water flowing over the edge of something, if it's flat, then you're not concentrating flow in a particular region, versus if it's not totally flat, where that constriction zone is, where the low point is, that's where you're going to have more scour, more erosion. So between the asphalt roadway running across the top and this relatively flat crest, that's probably what saved this reservoir here. Okay, so we looked at Blessing and we looked at Steinbach, which were kind of outside the R Valley. And now we're kind of going into the R Valley, which, yeah. No, they've kind of left it as is for now. I don't know what their plans are for it, since, yeah, I mean, I think it might be one of those things where probably it'll just remain unfixed. But yeah, because I think it's also privately owned and not state run. So they haven't fixed it yet. They didn't fill it, you mean like, like fill it back in with soil or something? Yeah. No, they just, because there was that big old gap, like if you go back to the previous slide, here, you can see there's this gap. They've just kind of left that thing in place, and they've not filled it with water or anything, and just kind of let it free drain. Yeah, I don't know what the plans are for that, but I can look that up and I can let you know. But I think for the most part, they've just left it as is, because the amount of damage throughout the valley was so much that I think in terms of rating what needs to get funds to fix first, in terms of getting people back into their homes, this was not as important, maybe as it was back when they needed it for textile production or so. Okay, so the R Valley, does that answer your question, Miles? Does it give you what you need? Okay. So the R Valley is where most of the damage occurred. And so if you look at the R Valley, you can see it's a pretty steep valley. You've got this relatively shallow rock that tends to be less permeable. And so when water lands on the hill slope, it makes its way into the channel very quickly. And it's also, the R Valley is known for wine. So the land use is such that the infiltration is relatively limited, and a lot of the water makes it into the channel very quickly. So there were some of the folks we talked to when we were there were saying it was like the water just arrived in a wave. It wasn't like the slow buildup. And so we actually want to look at see if there's some accelerometers to see if we can pick up some signal for perhaps like something that would be equivalent to a wave, like maybe coming through. But just to give you a sense, this is where the high water was on this building. So really deep. And if you look here, this is Altenar, the town, and the river actually runs through here and then goes up in that region. But you've got this old oxbow lake where people have built things. And then when the flood happened, it essentially just went round and filled everything up. Okay, and so one of the features that came up in terms of infrastructure performance is this when flooding happens, you have a lot of debris that's carried by the flood. And you get to a bridge and it gets stuck on the bridge. And so you're creating these temporary dams, essentially, that you get higher water, it's pushing against the structure. And so for a lot of these bridges, what would happen is the temporary dams would create enough hydrodynamic load to push the bridges off of their foundations. Like this railway bridge here was totally swept off its foundations. It's been demolished. This bridge over here, you can see that's also been demolished. And that's something in terms of this floodborne debris that gets stuck up against infrastructure and bridges. It's not necessarily handled in design code. I think there's maybe some beginnings of it in Switzerland, I think, but it's not a standard thing. Yeah. Could you speak up a bit? The army kind of wasn't good for my hearing. I think so. When you would design it, you wouldn't necessarily design for it to, like, you could try and design for transmissivity of the debris, but for the most part, what you want to design for is assuming there's clogging and calculating what are the hydrodynamic loads from that water pressing up against the bridge, so your connections are such that can resist it. Yes, yes. So that's actually a point when you look at, so a lot of these historic bridges, you know, if you look at like if you think about the quintessential medieval bridge, it's got these beautiful arch foundations that are pretty low to the water. But if you think about the water level rising, that's essentially, it has nowhere to go except through those pipes. So it blasts through with a higher velocity, it's more erosive, and you're directing it over the bridge and onto the surrounding infrastructure. So it actually, if you have more space underneath it, and we'll also talk about some other features later that you can do to try and make it that water can pass through more freely. But essentially anything you're doing that's constricting the space that water can flow when it's coming downstream, you're directing it elsewhere, and usually not in a way that you want. So yeah, that's a good suggestion, right? You just make more space. Okay, so looking at Altenar from bird's eye view, what I showed you here is that's these bridges that we looked at over here. And then what I want to talk a bit about more is this tunnel where you can see, so normally the RF flows around this way, but there's this tunnel that goes through here that ended up the water shortcut through it. And so if we zoom in on this area where the tunnel inlet is, so you can see normally it flows this way. There's these bridges, one of them's a railway bridge, and then the roadway goes through right here that's at a lower level. And so when the water got so high, it essentially knocked out these bridges, shortcut through here, and came out like a high pressure hose and washed out everything on this side. So these bridges were gone. You have a bunch of abutment scour, which we'll talk a bit more in a second. But let me show you what it looks like over here beforehand. You can see this is the roadway tunnel I was talking about, and you've got the rail and this other tunnel right here. That's beforehand. After the fact, you can see it's just totally swept away. And so here floodwaters have subsided. So you'll see, just keep this in mind, that's the high water level over here, which you can see on that structure. So pretty vast destruction. Here we're looking at it more closely. That's the same building I was pointing out. You've got, several meters of high water, and that tunnel level is about here. That's kind of where the water has to go in. So clearly, if the water's up here, it's going to flow through that tunnel, and the tunnel sits on the other side here. So looking at the roadway tunnel, if you look at it, so that's kind of where we observe the water level to be on the tunnel. And actually you could see, since, so a colleague of mine, the two of us are into scour and erosion, so we looked at these concrete panels that were plucked, probably not too dissimilar from maybe what happened at Orville Dam, where you've got hydrodynamic loads plucking out these panels. But you can see debris scratch marks from things getting carried through the tunnel. And here we're looking at, these are markers for the historic flooding. So the highest was in 1910, and this was this event. So just to give you a sense. So I mean, that's compared to the highest flooding, it's almost double. So this is the before. There's the spot, this is where the tunnel comes out. There's all this railway here. There's road going down here. There's some houses and some bridges. And this is what it looked like after the fact. So
That many turns through that turn, and nobody fixed it.
yeah, I think the thing about it is that that tunnel, like the flood level, because it's not that there was anything intrinsically wrong with the tunnel, it's that it could convey water through. And like this, the return period for this event, for example, is like it's estimated on the order of like 1,000 years or something like that. And if you think about when you're designing for earthquakes, like if you're thinking about like your maximum considered event, I think is like just shy of 1,000 years, and then you just want people to survive if the structure doesn't operate after. So it's just understand that this is the magnitude of this event is outside of anything in human recorded history. So let me just, I'll get to Miles first and I'll get to you. Yeah, what's it? Oh, when the water went through. So for the way for the tunnel to collapse would have to be that essentially the material around the tunnel gets eroded, or the support, like if some of those concrete supports in the tunnel got eroded, then it wouldn't have enough strength to stay up, kind of like a bubble underwater, right? If the bubble doesn't have enough internal pressure over what's the strength of the bubble, perhaps to keep it up, then it would collapse. But so in this case, it was pretty sealed, pretty tight, and the water just went through it like a culvert, like if you think about water going down to LA.
And like, one of the questions, why did they build a bridge on top of that, the massive rocks?
The massive rocks here. So, because if the rock is really hard, it's very expensive to excavate. And also they had homes up here, kind of sitting up on the hill slope. Like if you think about, like you've got your spot up in Gardner and you look down across the lake, it's nice to be up on the hill a bit. So they put this road up here so people can get through. They have a nice view down on this beautiful river. And also this rock is hard. It's a pretty hard, well-indurated slate. So it's hard to excavate. It got ripped out. Yeah, I'll show you some pictures of this in a second.
Who pays for all this?
That's a good question. Right now we get to insurance, reinsurance, government. And so that, I don't know the answer to that. I think if you're insured, you can claim from your insurance provider. But in many of these cases, people aren't insured, and then the German government doesn't want to pay to rebuild it, because like, well, if we pay to rebuild this and another event happens, then we have these losses. So it gets into this thing of like, because a lot of there's been people that have been living in these towns for generations and generations, and you say, no, you can't go back to your home. You have to move. It's very difficult. And so I think that's something that people in this valley, the German government, are going to have to deal with for a very long time. Because, I mean, yeah, it's the same way, like if there's sea level rise, you think about, well, we've been living here for a while, our livelihood is this, but then if it becomes inundated by sea level rise, it's really, yeah, I think, things are changing, and in a way that perhaps don't make for nice outcomes. So.
Is there any way that they would have considered, since that tunnel flooded multiple times, having essentially a vault door to close
Yeah.
it so that water wouldn't go through? I'm thinking about my hometown back in Pittsburgh.
Yeah.
It was in a low-lying area, and during the 1936 St. Patrick's Day flood, I mean, the whole place was just totally flooded up to the second floors. And eventually, they did install some sort of doors at an area where the water would have come through a small tunnel. It was a railroad overpass, but they blocked that off to keep that water from coming in. Would that not have worked here? Did they not consider it?
Yeah, I think certainly it would have worked. I just don't think they considered it. So I think the magnitude of the event, based on like when they looked at like that 1910 flood, and so it wasn't like, because they had recent events where it flowed down and it just went down the road, and they were like, oh, it's not too bad. And I think the thing here is it's the magnitude of this event was so large that, I think a lot of the outcomes people didn't necessarily look at. And I think also land use has changed since like 1910 versus now. There's a lot more augmentation of how the area is used compared to before. So water that might have previously percolated in and not made its way into the channel now gets transmitted through. And so it's difficult for these things because it's, yeah, I mean, when you look at it, people are trying to design for what's reasonable and then also what's affordable. And so it's a challenge. And I think now that this event has happened, I mean, I'd be almost certain that the flood design code for how you manage this is changed. But with these events, oftentimes it's like after the fact. Some things, like I think you can say were predictable and should have changed. And like, I mean, I think putting vault doors on there, perhaps, you know, that would have been an easy solution. I guess just at the time, like maybe the extent of damage from other events that weren't, like if you take a look at the event that was twice, like a half as high, it wasn't enough damage for them to go, oh, well, we should put a door on there. So yeah, it is difficult, but it is, like I think for these events, as more and more people will be, I think, becoming aware that we have to consider the interaction between how we build things, how we modify land, what the local geomorphology is, what the flood events are, how those change. So I think you can probably expect some changes in design and codes that will result in more expensive infrastructure, but ideally more resilient, right? Sure. So if we go back to this picture here, oh, this one's good. So here, if we look at this, so this water blasted out, and we'll look at it in a bit more detail on the next slide, but I just want to point out, you can see here's this more, you know, erosionally resistant rock, and you can see these really steep dipping joints in many of the valleys. But then here's the shear zone, potentially where material was eroded, and then a lot of just alluvial deposits. And so if you look at this, you can see that the water, when it came out, it couldn't erode here, but then kind of was able to really cut through some of these things where houses and all the underlying material was very easily taken away with these colluvial soils, which you'll also see in some of Yellowstone. And so to point out here, so that's the tunnel exit. You can see all of this has been destroyed, demolished. The bridges here were gone. This water treatment facility actually was destroyed too. And so when you think about it, not just the water treatment, but all of that, you know, wastewater getting into this river, now you've also got to deal with the environmental impacts of that. And so how you manage these types of facilities. And then something I want to point out to you just to notice in general is with a lot of these bridges, you would see that maybe the main bridge structure was okay, but where you have this interface on the abutments where you have your foundation sitting on the soil, you would see essentially bridges that were perfectly fine, but totally disconnected from surrounding land. And so in the R Valley, I don't remember the numbers exactly, they're in my notes, but I can't see them. I think it's 116 or 132 bridges in the whole valley. 112, so I was wrong on both accounts. I shouldn't go to Reno tonight. So 112 bridges, 63 were destroyed. And I think only 12 or 35 remained operational. And how many were damaged? 13. So you're looking about 30% remainder of bridges in this whole valley. So that's not ideal, right? If you think about the rebuilding cost on that. So anyway, so coming back to this abutment scour and foundation soil connection weaknesses. So here, this is actually in the town downstream of that reservoir that didn't fail. This is Iskirchen. You can look here, if you zoom in a bit more closely here on that zone. So we have an animation, and then you click it again, and you'll see this essentially, this armoring was totally undermined. So it's just hanging out there. The mortar, the contractor that put the mortar between those cobbles can feel good, but this is no longer serving as flood protection. And so here you can zoom in, you can see the same thing. And so this is another dam, just or a bridge slightly upstream, and you can see here also these zones of damage where there's erosion. And here you can see some temporary sheet pilings from when the foundation was initially installed. If you zoom in on that, you can see it's pretty deep. We didn't measure exactly how deep this was, but you can see as the water comes over here and cuts away, you get these plunge pools that just erode deeper.
So that looks like steel armor.
So these are actually sheet piles. So when they build this this foundation, they put the sheet piles in to help keep it dry temporarily while they get inside. And then when they're done putting the foundations, pouring the foundations, they just leave them in place. so as just to keep it dry during construction. So it's purely a temporary thing, but in this case, it helped protect the foundation. And so here, another example, you can see upstream side, you've got this foundation sitting here, and it's kind of closing in on the creek, impinging a bit on the creek. And again, these are small, like you can see, this is not, you could walk across this and not you'd essentially be wet maybe to your thighs. You can see erosion around here, and then this foundation can be remediated. In some cases, if you look here, this is scour erosion around this bridge pier, where water is flowing this direction, and as the water is flowing past, it has enough erosive power to kind of cut away the foundation materials. And so this used to be vertical. You can see where it used to touch there. So clearly that's a structural issue. And here, if you look, this is Marienthal. This is Darnell, close to Marienthal. This is a railway bridge. So it looked like before. Many of these homes here were swept away with the people inside them. And if you look at this bridge, so this foundation, it's a really beefy foundation, totally inoperable at this point. When we went back, it was taken out. You can see here, this abutment's pretty good, but because you're impinging on the channel, when the water levels rise, the water has to go somewhere, and so it has to go around, and so it carries off the sediment around the wing walls. Okay, so this may be a bit like Monty Python, something completely different, but not really. So this is the flooding in southern Montana, Yellowstone, that happened in 2020. And so this is, again, a warm rain on snow event. You had a pretty large snowpack hanging out in the Beartooth Mountains in June, and then you had this warm system come in, dump a bunch of rain, so you had a lot of runoff. And so this is Red Lodge, and you can see here, this house is demolished. These utilities, similar to what happened in Germany, you have these utilities that just get exposed as the material gets eroded. And these deposits here, these were not here before. These are like cobble, boulder-sized deposits that got moved. When we talked to people that were there, they were saying that they could hear, standing next to the river, where you could hear the rocks just kind of pounding and rolling over each other as the floodwater came down. And so just to orient you, so here we are at Sunnyside Lodge. Here's where we are. Yellowstone is down here. So you've got Wyoming and Montana. And I'll be talking about, so Red Lodge a bit, where there was a lot of damage. And then I'll also talk a bit about the Yellowstone River here. You can see, so these are the Beartooth Mountains here. And there was a lot of snow. And rain falls on this. And the water drains down these little drainages naturally. And if you looked at a map and you looked at the drainage, you go look downstream of the drainage and there'd be damage there. The saving grace in this case is a relatively sparsely populated area, so the amount of damage relative to amount of flooding is not as substantial, but still, pretty large economic impact. Okay, so similarities here, and again, like for Yellowstone, I'm going to talk about. Let's see how I'm doing on time. Similar to, if you go back to that previous one, similar to what we had in Germany. Again, it's this interface between your foundation and your soil. You can see here massive bridge abutment erosion, and also debris dams, where debris gets stuck up against it, pushes the bridge off of its foundations. And if we look at this is in Red Lodge. This is Rock Creek, so it flows this way. You can see here's this bridge that looks like it did pretty well, but if you think about the design of this thing, it's constricting the channel. You've put this bridge to naturally make where the river can flow smaller. So now if you have higher flows, you're going to get higher water underneath this thing, which could impact the bridge, make it more possible to get debris traps, or you're directing water around it. And you can even see here in the case, this bridge is sitting around a bend. There's some flow straighteners in here to try and make the flow not go directly at that abutment, rather bend it around. But you can see here, there's much more erosion here, much more scour. And during the flood event, the water also worked its way around here. You can see this wall over here. I don't have a picture of it, but I guess you can see it up here. There was quite a bit of retaining wall failure there. Here, most of the erosion is happening on this side. So feet of erosion over there. This is now getting to the Yellowstone River. This is Tom Minor Bridge. This is what it looked like in September before the flooding. Bridge is hanging out here, and this is during the flooding. So you can see it's gone at this point, but it's also a narrow point in the channel. And again, here you see these abutments that have these wing walls on them, these kind of side pieces that are supposed to help resist erosion, which is a good idea. But you also, at least from what we're seeing, is you don't want to put those abutments into the channel. Rather, put them outside and then still have that protection against erosion. And so if you look at it, here's the bridge superstructure that ended up over here, downstream, and the abutments are still there. And so I don't have pictures of this, but we end up doing a bunch of sonar to map erosion within the channel and looking at scour and flow panics. Anyway, so similarly, exposed utilities. You can see flexible utility lines sitting over here. And in this case, you've got the river kind of flowing this way. So it's always going to erode on this bank. And so if you put the utilities there, I mean, again, the amount of erosion is on the order of like, 10 to 20 feet. So it went a long way. But these utilities, you have to think about where you put them. And oftentimes utilities run across bridges underneath the bottom. So if your bridge goes, then your utilities go. But then you might think, oh, well, let's put it underneath the channel. And this picture, which seems kind of like, oh, what am I looking at here? You see that concrete poured on there and the sandbags? This is actually remediation for a sewer line that runs underneath the Yellowstone. And so all the sewage from Yellowstone comes through this pipe and gets processed in Gardner. And so they were worried that this line was potentially impacted due to these boulders smashing into this thing. And so we did some sonar to try and look at the impact of this. But ultimately, that sewer line was shut down because if you think about that sewer line bursting, now you've got raw sewage going into the Yellowstone, where the vast majority of business here, I mean, beyond the environmental impact, which would be horrible, it's also this whole community's livelihood is destroyed because nobody wants to eat poopy fish. So it's like, this is again an example of thinking about how you site these things. So this was shut down, and I don't know what they've done with it since then. Anyway, next slide. And so kind of something that I've hinted at a lot so far is this interaction between geomorphology. I should stand here so I don't block you guys. You can see my bald spot. So there's these geomorphological controls on infrastructure response that you have to consider. And so here, this is looking at Cinnabon Basin Road Bridge. This is again near Gardner, just kind of northwest of where I showed you that previous image with the sewer line. And so here you can see this bridge abutment has some erosion here. And so if we zoom in on that, you'll see here's this pile exposed, and this foundation structure has been undermined. But if you look at this material as well, it's these colluvial deposits where you have cobble in some sand and some clay, which is a very erodible deposit. And so in this case, this was a campground where they had it situated near this bridge, and the campground lost 30 feet of shoreline during this erosion event. So next slide. And so here, this is kind of what I'm getting at with this stuff, is that if we're going to look at infrastructure, we kind of have to do this more holistic approach of the flow, interacting with local geomorphology, interacting with the structure, and designing these things together. And so here, if we look at this bridge, like, okay, this is after we came back for a second phase. Here they've dumped some material to help protect that abutment. But if you look at this, what we did is we took some drone imagery, and you can also, we did this with some imagery that people collected after the fact. We used those videos, and with our post-disaster reconnaissance data, we mapped that onto that so we can actually scale what we see for flows. And here you can see that in this portion, there's a substantially faster velocity, which is going to give you more erosion. And so if we look at this next portion, you'll see this is showing a bird's eye view of the same bridge. You can see the bridge here, and here's the river running this way. Here's that abutment that was damaged. And so what I've overlain on this image here is this multispectral index, where you're taking several pictures that are just measuring reflectance in different bands of light, like how strong is it reflecting in green, in blue, and red, etc. And so we did some experimentation here where with these multispectral indices, we're able to identify different types of soil deposits. And so here you can identify the gravel bar. And also, I mean, we kind of knew before because we walked on here, we want to see if you can map it. So here's this gravel bar, which is going to be substantially less erodible, it won't move as easily as these materials that are embedded in the sand. So before you build this bridge, if you looked at this site and you saw this gravel bar, you'd already know that over here, it's going to erode more. And so you've kind of built this as your fuse in your structure. That's what's going to go. And the point is that, you know, I mean, I don't think you can fault the people for building the bridge this way because it's not been the standard. But when you look at it, if you consider how the flood flows will interact with local geomorphology, and you can map this with remote sensing with drones and this kind of thing, and potentially with satellite imagery, looking at, well, where are potential hotspots where we should be looking at to perhaps do remediation? Or if we're going to put in something new, where is a spot where, okay, that's not going to be a good place to put it? Or you could use nature-based solutions where you say, okay, well, I don't want it to erode here, so let me pop a different type of sediment or something in here that's going to try and leverage a different type of geomorphological response. Another thing is that, so with this flood mapping, oftentimes you can't access different areas. And so when you look at flooding, you want to know how deep it is, right? But if an area is inaccessible or it's, you know, unsafe to get up to a structure, you have to walk up right close to it. And so if you look at this picture of this structure in Germany that was flooded, maybe this one, like you could kind of guess roughly where the high water is. But so we did some experimental deployments here. We use the same multispectral camera, which is normally on a drone, but like I said, we couldn't fly drones. So here's a colleague of mine, Nina, holding this multispectral camera that has these 6 lenses. And she's taking photos with it, and I'm just walking behind her holding the battery pack. But so, yeah, you gotta play to your strengths. And so here in these images, I guess in this projector it doesn't show as well, really you'll believe me is that so these images are the 6 different images you get from the multispectral sensor, where these are just the XY pixel indices, but this is showing reflectance in the blue band, this is reflectance in green, red, etc., and then this is a thermal image with lower res. But so that's what you get out of it, and based on these reflectance characteristics, you can actually combine these bands and automatically extract where the high water was. So this is some preliminary data, so this is some ongoing work. But the point is now you can avoid sending people into the field to go and look at this directly. You can dispatch drones and map a much larger area and kind of adaptively figure out where you need to go next. So you can map spatially varying flood extent and severity. So this is ongoing work. And so the point behind all of this, because I spoke to a few beforehand, I'm actually a numerical modeler. I spend most of my time sitting down with a keyboard, but this other work's a lot more physically engaging, I guess. But so the point is that we can use these high resolution data sets where if you think about an earthquake, you have accelerometers, you can measure the shaking. That's your demand parameter, the accelerations on the building. But for flooding, if we can use this post-disaster recon paired with this video where we can extract the flow velocities, the flow depths, and look at the local geomorph, we can actually come up with comprehensive descriptions of specific flood events. And we can use those to calibrate these numerical models, where this is just some simple ones where you can model the fluid flow. This is like a bridge pier. I just ran these are pretty simple, quick ones you can run. But so you look at this could be debris that you could take that model, couple it with this one, look at debris getting pushed up against the bridge. So this is some work that I'm trying to get started up here. Additionally, if you want to look at erosion, so we've done some work looking at rock scour and rock erosion, similar to what, like if you look at the concrete panel eroding in Orville and also the emergency spillway, if you try and model that, you can get these 3-dimensional flow structures of these vortices in the water and how this block erodes. And that block erodes now changes the flow field. Something else over here might get eroded. Similarly, we can couple it with soil models where we have a fluid model and we could look at how is sediment transported. Like if water is flowing over this, where is the sediment getting carried? So ultimately, this field data that we get out of it, it gives us a way to actually analyze the impact of extreme flooding to the point that we could design to meet these different events, as opposed to using maybe historic data that is getting more and more dated and not capturing these site-specific effects that contribute to making a flood more or less destructive. And so just in summary here, flooding response, it's a system. You have to look at things comprehensively. So to understand it, we have to look at this infrastructure natural system. We have to capture geomorphs. So hopefully I've convinced you of that in terms of these colluvial deposits. Those are not good, or how things will, well, I shouldn't say they're not good. That's maybe too much of a blanket statement, but they will erode quickly. And where you site structures, this will make a big difference. And so you have to use your knowledge on these different aspects and ground truth your numerical analyses, which will give you anything you want. You have to ground truth them against real observations. And so to design resilient structures, we have to do this comprehensive type of analysis that looks how things are changing based on climate change, using what we have from previous observation, and then trying to predict system change, and potentially trying to use some of the things that I've shown here that made some structures perform worse to actually help them perform better. And so with that, just want to acknowledge there's a lot of people involved with these different things. But so for the, yeah, especially Nina Stark and Anna Limnitzer had a lot, they were the German collaborators for the work in Germany, and then also in Yellowstone. So with that, one more slide, just thank you. Here's the folks that worked on it. And yeah, there's Yellowstone, not a bad place for field work. Oh, you're not saying.
One thing I get out of this is that it's easy to think with bridges, oh, just rip it down, replace it, bring it higher, and increase the flow that way. But what I see your work showing is more opportunities to kind of harden an existing structure and redesign the bridge abutments so that they're more hardened for extreme events. Right?
Exactly, yeah. So because I guess, you know, if you look at it like what we're showing here is where it fails and what drives those flows. And then where you choose to go from there, I imagine it'd be the same way where you're like, okay, option A costs X. And yeah. We're like, okay, let's dig it out and stretch it out versus, yeah, hardening. And, you know, is it going to be enough where you just put a whole bunch of riprap, a whole bunch of large rocks, and then hardened surfaces? And so that's I think where, when you look at these things, what you would have to do is some type of analysis that tries to capture the variability, how your different remediation options will address specific events, and ultimately what are your goals? Because if you're going to design for the bulletproof, everything's going to be good. It's the same way like if you design a building for an earthquake that's going to resist everything, nobody's going to build it. So yeah, you kind of, I think there's a lot to learn from earthquake engineering in this sense that could be applied here in a similar way. Yeah, you just get it and then I'll.
I'm thinking of the floods just over the last week in Southern California. And so much of the damage was mud flows, you know. It doesn't look like the German example there. I mean, all of the damage was where the water moving in the channel or expanded channel was. But does any of your work address the damage or how to protect infrastructure from the kind of flooding and mud flows that happened in Southern California?
So there's some work that I'm trying to get started up that if NSF nods and says, yes, we'll give you money, then there'll be some students working on that. But we're looking specifically at, so for a lot of these debris flow models, if you look at like for example, post-wildfire debris flows or, you know, I guess rainfall triggered debris flows, for a lot of these types of events, they're empirically calibrated based on observational data. And so what's out there is people will have like a probability of debris flow happening, but you don't necessarily have a sense of where it's going to go. So the work that we're proposing to do would use, kind of like on that last video where I showed that soil kind of sliding down, we're using three-dimensional models that describe the essentially debris flow triggering and then also have flows downstream. And the idea behind that is we take these numerical models, and again, you compare those numerical results with physical observation and make sure you're actually capturing what's happening, and then use that to generate a whole bunch of numerical simulations that would allow us to capture the uncertainty and how far these things would go. So then I think, is that something that overall the debris flow and also post-wildfire debris flow community is moving towards, is looking not just at potential of something happening, but spatially varying hazard for these events. Yeah. You had a question?
Yeah, so for these
bigger events in climate change, do you know if the like a lot of work I do is like principal maximum flood related, and are they calibrating that in terms of different types of storms that are coming in? Because the principal maximum flood's pretty cool.
Yeah, to be honest, I'm not sure how they calculate these things, but if you want, drop me an email and I'll ask a buddy of mine at DSOD that'll tell you exactly what they're doing to meet these things. Because for example, like for Orville, I think they're also trying to see how to update these things, but I'm not gonna lie. So if you let me know, I can get that info for you. Sure, sorry, I don't know the answer.
Caltrans is designing for 200-year flood for the.
Are they recalculating?
Yeah, good question. It depends exactly which organization you're looking at. Some of them are calculating like the design storm as they're making their standards, and some of them you longer they're using data.
So in Trout Creek in South Lake Tahoe, I was involved in a bike trail bridge over Trout Creek, and the modeling for the design storm event, I don't remember what year it was, but it required new predictions for modeling, and it's a wonderful bike bridge in this very cool place, but it is way in the air. And the neighbors were hoping that the effect of the bridge, the visual effect would be a lot lower and it would fit in the landscape better and it would be, but that isn't what happened. The bridge was like way in the air. And this last year, with all the flooding, I've seen aerial photos of that bridge and it's beautiful and it is serving as a bike trail, and the entire Trout Creek meadow is water. And usually, the channel is not very wide. And so I think that was pretty effective, but that was a requirement for them to do it to that level because it wouldn't have been done otherwise. I don't think it did its job.
Yeah.
Whereas last year.
Yeah, I think for a lot of these things, money talks, right? And I think kind of almost in the beginning, if you look at insurance and reinsurance, pessimistically, I think the people that will drive the decision making will be the people footing the bill when damage happens. And so I would suspect that at some point, the insurance can't say we're not going to insure anybody anymore. They would have to update the requirements and push that way. So, but I think that's a very interesting space. If you start looking into policy, who pays for what, who mandates what the requirements are for survivability of these different structures. But yeah, that's well outside my scope of expertise. Yeah.
I don't know, we mitigate floods by like the next what maybe or like things to or sort of infrastructure stabilize even if we're like action.
Is more about the what, the last sentence? No, I think and I think for the type of solution that would work, it's going to depend on the site. And I think when you go and look at a site, the first thing you have to do is try to develop a geological and biological model for what's going on and seeing what controls the landscape evolution over time. And then take inspiration from how those specific local features are impacting landscape evolution. Because apart from mitigating the hazard posed by these events, you also want to minimize your environmental footprint. So if you use local nature-inspired solutions and try and look at also the local landscape evolution, that's, I think, how you could look at, like in a coastal environment, maybe there's different mollusks or something like that you could use, things like that to provide better resistance or different types of dune grass, who knows. So, but it's going to depend on where you are. That's at least my thinking on it. Yeah.
Like the earthquake building, whether it's like flexible maybe.
Yeah, so I think that kind of gets to this gentleman's question here, right, where it depends on how much you would kind of have to look at what are the consequences of a failure, and for the different consequences, what is the cost of the remediation to mitigate that? Because in some cases, like if it's a lifeline that has to stay open, you know, then the cost becomes less important. And like if you think about like for example, in the Bay Area, if the Bay Bridge gets knocked out, that's pretty bad for people being able to evacuate and things like that. So there you really like the tolerance for failure is much lower in something like that. And also for dams, like if you think about a dam failing, the tolerance for failure for that is very low. Because if a dam fails, you've got potentially, you know, tens to hundreds of thousands of people downstream at risk. So same thing for these bridges, you kind of have to look at them like, well, if this is what I want to be able, after this type of event it needs to be operational, these are different solutions that would work. So maybe you just put some additional erosion resistant repairs kind of further out from the channel. Because if the bridge is already there, you don't want to rip it out and kind of expand it out. Maybe you just try and redirect the flood waters in a way that maybe dissipates it or puts it in a spot where erosion's more bearable or acceptable. So it'll just depend on the situation, because it's always this trade-off between consequences and cost to fix it. The same way, like if you look at, for a lot of dams, you know, there's like dams have this unfortunate feature of being built along faults, because oftentimes faults give you these really beautiful linear valleys that you can put water in. And so there's these dams that are built on these faults. And so folks have to go around and every year go and look, well, what's the hazard posed to these dams? And there's a plot where like, you know, probability of occurrence and consequences of failure. And they have to look at these different events, whether it's an earthquake or an extreme flood, and figure out, well, based on these things, this event over here is the one that poses the biggest, you know, risk. And we only have X amount of dollars, so that's what we're going to fix. And then if we can come back to it in a year or two, then we'll try and fix this other thing. But there's finite amount of dollars and in many ways infinite numbers of problems, really. Yeah. Yeah.
So in California, the leading climate change models are predicting an approximate 60% increase in precipitation during extreme flooding events. And I'm wondering if you have any good low-hanging fruit recommendations for flood vulnerable communities, either on the coast that are looking at a huge increase in absolute rainfall during these extreme floods, or the drier communities that are looking at a huge relative increase in their extreme floods.
Right.
Hopefully a
What's that? Is a fun question. Yeah, no, I mean, I think that's a difficult one in the sense that, so oftentimes the most exposed communities are also the most underfunded communities. And so how you address those in terms of, because what was the first one you were asking about? Communities that have like sea level rise or something like that. Was that what you were saying for the first one, or was?
We'll see the largest absolute increase.
Oh, right. Yeah.
Expecting this much, getting this much, but they're expecting a lot more than like the Bakersfield.
Yeah.
The Dallas and the Valley areas, so either
Yeah.
one.
I think, you know,
Good.
yeah. Yeah, no, I think for those cases where you have more frequent events that are just bigger events, you know, like I think you either have to, like you could move, which is not a nice solution, right? That's not a good solution. You think about like a lot of like, so that's like the worst case, but you think about like easy, just pick up and move. Yeah. But then if you have to like, I think the best thing that people could do is you have to go talk to the people that are making decisions about where money goes to fix things. Because if these communities, like nobody wants to leave their hometown or leave your house. I mean, that sucks in all, like whether you're rich, poor, nobody wants to leave their house. But yeah, and so, yeah. So, but I mean, I think ultimately you have to go talk to people that are making decisions about mitigation measures, because any of these events, just the astronomical cost associated with trying to mitigate for these types of events, and especially if you're thinking about not just like in the next 2 years, but you're trying to think in the next 50, 100 years, you have to try and influence people that are directing where money goes to do things. And so, yeah, I guess I don't have a nice silver bullet other than, bother politicians and vote violently. Not violently, that has a bad connotation. Vote, yeah. I don't want to make political jokes, but you want to vote consistently and always. But and I think for these events that happen less frequently, I mean, you could try and look at, I mean, those are difficult because it's also, there's less data to predict on. And the short answer is, I don't know exactly, but I think really, at least where research is going, that could try and inform these things is because right now there's so much uncertainty. And so if there's a way to generate data that provides insight into potential outcomes and how things can change, there's no absolute answer, but to provide bands for design, like uncertainty bands for design, I think that's how you have to go at it. But really, you have to go after people who can help provide funding to make these things happen. So yeah, register to vote and vote peacefully and calmly, but consistently. So, what's that?
Thank you, Mike.
Well, thank you.